I mean to show that there are certain logical contradictions and absurdities at the very heart of algebra and modern mathematics. That the very essence of algebra is confounded with certain logical difficulties that result in their opposition to certain perceived restrictions which Euclidean mathematics placed on that discipline. Now, I have mentioned a few of these, such as that five is not divisible by 2, since 5 is an odd number, and odd numbers are not divisible into equal halves, for that is the very definition of odd numbers. And because in dividing an odd number into equal halves, you would simultaneously be dividing the unit, which is by definition indivisible and without parts. Now, many would say that such a procedure would only contradict a definition which may or may not be agreed to, such as that the definition of odd numbers may be something else, or that we may not distinguish between odd and even. In fact, to oppose that restriction, you would have to refuse the differentiation of those kinds of numbers. You'd have to refuse that there is any essential difference in kind between odd numbers and even numbers. And as I have said, in practical calculation and computation, there is no distinction between kinds of numbers, between essential kinds within arithmetic. The procedures of calculation compute quantities irrespective of the definitions of odd and even. Indeed, we might find just that algebra has always been a sort of computational device, and so was meant at first and has always had the sort of motive of ignoring essential kinds, whereas Euclid means to the purpose, the entire project of Euclidean mathematics is to prove of the kinds of numbers as well as of the essential kinds of shapes, what their essential properties are. The whole purpose of Euclidean mathematics is to prove of the kinds of numbers and the kinds of shape what their essential attributes are. That is something very different from calculation, something which you cannot do within the manipulating the signs of equations. These definitions are perceived as merely getting in the way. Hence, these things are sort of peeled off age by age. Yet they are still taught as having some significance. I've said this also already, that students are still taught that certain numbers are divisible by some and yet not divisible by others. They're still taught that there is an essential difference between odd and even, that those are certain kinds of numbers, and that there's an essential difference between primary and composite numbers. Those are the sorts of things which Euclidean arithmetic is concerned. Yet students are still taught to divide a number by a number it is not a multiple of and is not divisible by. So those sorts of restrictions or perceived restrictions that are placed on or are perceived as imposed on or as having been previously imposed on mathematics, that is the perception of algebra in modern mathematics, that those are just restrictions of the procedures of calculation. They're not opposed on principle. Now those examples are the rather peripheral and almost secondary, those definitional restrictions, which make it impossible to perform certain calculations since they would contradict those definitions, are seen as merely resulting, they're seen as not really contradictions because they don't agree with the definitions that they contradict. They're seen as something, those definitions are seen as something that can be done away with while mathematics continues unhindered, or that mathematics may even continue. But there are even deeper definitional propositions which algebra also is wont to overstep and ignore, in which those definitions are sort of drawn from. And these deeper restrictions, these deeper definitions that are never directly dealt with, are not such as you can choose a different definition or choose to ignore them. They're at the very basis and essence of even quantity. A different definition of numbers, I don't think could help you here. Another one that comes up is that a number is not divisible by a number it is not a multiple of. If a number is not a multiple of a number, it is not divisible by that number. These concepts arise because of the Euclidean idea of what numbers are. They are seen as composites of irreducible elements. The primary numbers, the prime numbers, are seen as elements being things irreducible. Hence the unit is claimed to be without parts and indivisible. And out of such irreducible elements, composite numbers are composed or consist. The composite numbers consist of irreducible elements and are divided back into the irreducible elements. Whereas today, in algebra and in modern mathematics, numbers are thought of as points on a line, on a continuous line. Again, we find the distinction between continuous and discrete, where numbers have no interval. Whereas numbers have no interval and are not along a continuum, while the other species of mathematics, the continuous, is infinitely divisible, being an interval. The concept of number today is rather crude, as being either numbers being along a line, but also being composed from addition. They are not irreducible elements, and they're not seen as wholes and parts. In Euclid, a number is a multiple of a number if it is measured by that number, such as to have that number as a part. And a number is a part of a number, of another number. It is a multiple of, if it measures that number and is a part therein. They're seen as wholes and parts of composite numbers composed of irreducible elements and primaries. Now, again, at face value, someone might say, well, we might just ignore that definition and choose another and let a number be divisible by a number it is not a multiple of. But I think we will find that that conception specifically will prove to be a sort of hinge upon which this sort of contention rests. When we consider the two more foundational concepts about which the contentions between these two paradigms of mathematics arise. Those two concepts are incommensurate quantities, incommensurate magnitudes, and heterogeneous quantities, or quantities of different kinds of units of measure. These are like two degrees of the same, so to speak, in the modern terminology. They're like 2 degrees of the same idea regarding what can and can't be compared, and therefore also what can and can't be multiplied and divided by each other. Incommensurate magnitudes are defined by Euclid as magnitudes which have no ratio one to the other as any number is to any other number. There is no common unit of measure between them. They cannot be directly compared. This is where irrational numbers arise, where these sort of paradigms clash in regarding what is permissible and not permissible, and what is an approximation and what is exact, and what can and can't be definitively reached with exactitude. But Euclid, I should mention again, the idea of incommensurate quantities did not arise in his 3 books of arithmetic. They arise in his dealing with continuous magnitudes. That is important because in Euclidean arithmetic, there are no irrational numbers. We don't even find fractions in Euclidean arithmetic. We don't even find decimals. There are no negative numbers. And these things only arise in arithmetic when dealing with measurements and calculating measurements of lengths and areas. Hence, he defines incommensurate magnitudes, and he's speaking about lines, not numbers. But this is where irrationals and irrational numbers come about. The common example is the diagonal of a square. The diagonal of a square. The diagonal that bisects a square is incommensurate with the side of the square because they have no common measure. And you cannot say that one is to the other as any number is to any other number. There is no part, however small, of the side of the square which the diagonal is also a multiple of. Such as that if you divide the side of a square in half, and you divide the half again in half, and then you divide that in half, such as to try to find a part of the side that goes into the diagonal a definite number of times, or which is a common measure of them. You can never find such a part. The 16th part of the side of a square will not go into the diagonal a definite number of times. This is why you cannot establish any relation between them. There's no ratio. They're irrational. The diagonal is irrational. And since lines are infinitely divisible, you can divide the 16th part of the square. Then you have the 32nd part of the square. That goes into the side 32 times. That will not go into the diagonal any number of times. It will fall between two numbers. And you can divide the 32nd part of the square and the 64th part of the square. You can divide them. You can divide the side of the square into lesser and lesser parts. Which the side of the square is a multiple of and is measured by. But however small you divide those sections, no part will also measure the diagonal. And there will be no part, however small, and you can divide them ad infinitum forever. There'll be no part, however small, of the side of a square which the diagonal of the square is a multiple of and is measured by, such as you can say that one is to the other as some number of the given part is to some other number of the same given part. That is where irrational numbers arise. And algebra and modern mathematics have an even greater difficulty with this. This is why this is more a difficulty for them, because they operate entirely with equations. Whereas Euclidean mathematics operates entirely with ratios and proportions. So we are not pressed to calculate any of those quantities. But since a figure or a surface can only enter into an algebraic equation insofar it is considered as the product of quantities which are lengths, and as far as the shape or the figure or the surface is not insofar as it is a shape of a certain kind, but only insofar as it is a quantitative area thought of as the product of the multiplication of certain quantities designated by the lengths of some lines. Since those arithmetical procedures of multiplication and division are inherent in the representation of figures and lines in algebraic notation, these incommensurate lines are required to be expressed as the products and quotients of other quantities, and so demand a final calculation. In Euclid, they're just lines. There's not a decimal that goes on ad infinitum, because the diagonal of a square is just there as a line. It has no ratio. It's irrational. It has no ratio to the side of a square. But within the paradigm of proportions and ratios, Euclid is almost able. These are restrictions as to what is allowed in arithmetic. But Euclid is able to even say, well, the side of a square is not to the diagonal of a square as any number is to any other number. But if we take that diagonal, which is simple, we just take the compass, and the compass we put at the ends of the diagonal, and then we erect that perpendicularly with the side of the square. Then we have a rectangle. We construct a rectangle out of both of them. They have no ratio. But we can make a rectangle out of them, and we can see, well, what if we cut the rectangle so that the square was the lesser part of the rectangle? The base is already the side of the square in question, and the length is the diagonal that's irrational. And we constructed a rectangle from those. Why don't we cut the diagonal at the length of the side of the square? And then we have the square and the diagonal protruding on the same base. Then we can almost say that the base is to the diagonal as the square is to the rectangle. Things of the sort of that nature. Even though no numerical quantity could be given, and that is an irrational line, or irrational quantity even, but does not need to be expressed as a definite quantity. It's just a line that's there, and we can construct things upon it. Whereas if you're working with equations, everything that factors into an equation, whether it is a surface, a figure, or whether it is a line, can only be related in the equation and take place in the algebraic notation insofar as it is a multiple of some other quantities, such as lines, or insofar as it is a quotient of some surface. Hence, they're almost required to compute their numerical value, which they have no numerical value. They have no definite numerical value, given any unit you can find on the side of the square. These are indefinite. Essentially, the irrational numbers are indefinite. The indefinite was one of the principles of the Pythagoreans. The Pythagoreans said that the principles of everything are the definite and the indefinite. And the indefinite was the principle of indefinite plurality. These corresponded to the principles of the one and the many, or of unity and multitude. The definite and the indefinite. The indefinite was a principle not of multitude, but of indefinite multitude, which can't be comprehended. Whereas numbers were the offspring of both. Of the definite imposing limit on the indefinite. Hence, there's no answer. When you're looking for a numerical value, there's no answer. When there's no definite quantity there to be found. There's no definite quantity at all to be found, such as pi. With the example of pi, the ratio between the radius of a circle and its circumference are similarly incommensurate. The circumference is incommensurate. And when we try to find that ratio and by a computation, you get an irrational number that is through and through indefinite. Hence you can say, well, I can tell it's somewhere between 3 and 4. But it's not 3 and it's not 4, but it's somewhere between them. Some would stop there, but then you can say, okay, well, it's somewhere between 3 and 1/10 and 3 and 2/10. But it's not 3 and 1/10 or 3 and 2/10. Somewhere between them. Then you can say, well, it's somewhere between 3.14 and 3.15. But neither of those themselves. And then it's somewhere between 3.147 and 3.148. And it will always fall between any two definite quantities because it is indefinite. That it is not a definite quantity whatsoever. And you can continue that computation ad infinitum, and it will always fall between any two definite quantities because it is essentially indefinite. Just like the diagonal of a square. You can cut the side of the square into lesser and lesser parts ad infinitum forever. And you will never find a part that goes into the diagonal. And if you find a part that goes into the diagonal, that does not go into the side of the square. Hence, when I said a part, I mean a part which the side is a multiple of. That you reach by division. You divide the side in half. Then you divide that in half. Then you divide that in half. Those are all parts of which the side is a multiple. None of those parts. And you can continue that process forever. People don't realize what that means, forever. And you would never find a part, however small, that goes into the diagonal. Or that the diagonal is a multiple of, that is also a multiple of. This has to do with the infinite divisibility of the continuum, of continua, of lines, as opposed to discrete numerals. Hence, again, the confounding of those two species of mathematics is where much of this arises. Now, that is just where the difficulties begin for algebra. I said that there were two concepts that I thought sort of corner algebra into making absurd maneuvers. Incommensurates were the first. Mind you, those were between lines and had nothing to do with numbers, but give rise to irrationals and irrational numbers in a roundabout way. But they don't for Euclidean mathematics. The second concept is that of heterogeneous quantities. Quantities of different kinds of units of measure. With incommensurates, there was no common unit of measure. But that was even between lines. That is to say that even within quantities of the same species, such as lines, even between lines and lines, some of them have no common measure. There can be no definite ratio between them. If they're such as that they're not proportionate. They're not proportionate. There's not a proportion between them. That's even between lines, which are the same species of magnitude. They're the same kind of quantity. The further step is in heterogeneous quantities. Quantities which are different kinds of units of measure, which have different kinds of units. The question isn't whether, they fall, it's indefinite because it falls between this quantity, and then when I specify more and more, it falls between any given quantity, and it's indefinite. Because it's a little bit more than this, a little bit. Between heterogeneous quantities, no ratio can be drawn or even attempted because they're of different kinds of units of measure altogether, as between lines and surfaces, as also between distances and times. Now, algebra was designed for that purpose of comparing and equating different kinds of quantities with different kinds of units of measure, such as distances and times. And before venturing on to those incomparables, the first maneuver of algebra was within geometry. The first maneuver in this direction was within geometry, of establishing equations within geometry to express that the area of a figure is equal to the numerical value of the area of a figure is equal to the product of the numerical values of certain lines. You will find that this is just why the fact that difficulties arise here is precisely why in Euclidean mathematics neither lengths nor surfaces nor bodies are given numerical values and no calculations are performed. There are no equations. These difficulties I'm getting to are why that is so. And again, now looking at heterogeneous quantities, we come back to that statement I made that a number cannot be divided by a number it is not a multiple of. That sort of concept is very relevant to this issue about performing calculations between different kinds of units of measure, between different units of measure altogether. For a distance is not a multiple of quantities of time. A distance is not composed of quantities of time. What sense, then, could there be in dividing a distance into times? Or a surface into lines? Now we're getting near to the sort of claim I want to make. I have composed a sort of reductio ad absurdum, but we're not quite there yet. And this is still a work in progress, an open investigation. Does it make any sense to multiply quantities of lines? Does it make any sense to multiply a quantity of length into an area, or to divide an area into quantities of length? Those are not the same units of measure. Length is a different unit of measure than areas, than squares. For if you take a surface, suppose there's a surface, such as a square or a rectangle. Suppose there to be a surface. Let the surface be divided in half. You obviously agree that the area of a surface may be divided in half. And that would be a sensible way to think about dividing the quantity of an area. A surface indeed may be divided in half. Let it so be divided. It is divided then into two lesser surfaces, two lesser areas. Then divide one of them in half. That then is divided into surfaces and not into lines, into lesser areas. Divide the part. Divide then the surface into which the others were divided. And you get an even lesser parts with an even lesser area. But you always get a surface. For a surface may be divided into two smaller surfaces or areas. An area might be divided into two smaller areas, which may then themselves be divided into smaller magnitudes, and so on ad infinitum. They're infinitely divisible. Again, the continua and the difference between continua and discrete arise again and again. They are infinitely divisible. The surface, the area, is infinitely divisible. You can divide it in half into two lesser surfaces or areas. Then you can divide those in half into areas of a lesser magnitude. And they are infinitely divisible and always only into areas or surfaces, but not into lines. And however many times you divide an area or a surface in half, you will never reach a quantity that is less than a line, nor that is equal to a line. You can divide a surface in half ad infinitum. That means forever. Forever. You can do that forever, and you will never diminish its magnitude to anything that is less than the magnitude of a line. An area, when divided, and divided again, can never become less or equal to a line. How then can a surface be a multiple of quantities of length? How can an area be a multiple of quantities of length? For Euclid says that magnitudes have a ratio to one another which are capable, when multiplied, of exceeding one another. Which are capable of exceeding one another. But you can divide an area into lesser and lesser areas ad infinitum. While the line, that is the base of the area, will never exceed the magnitude of the area, however much it is diminished. How then can there be a ratio between them? How then can the area be thought of as a product of quantities of length, or the quantities of length as quotients of an area? Again, this regards that statement that a number can only be divided by a number it is a multiple of. It is like the inverse statement, the congruent and inverse statement. If a surface cannot be divided into lines, for a surface is infinitely divisible into lesser and lesser surfaces, how can it be a multiple of lines? For they are different, they have different units of measure, and they must. Because if there is a square with the side of 2, with the numerical value of 2, if there is a line with the numerical value of 2, and that is squared, suppose then that the product is the area of the square with the side of 2. Suppose that its area is 4, as we commonly believe. Having the numerical value, having a side with the numerical value of 2, its 4 sides will have the numerical value of 8. 8 units of length. But then the numerical value of the perimeter would exceed the magnitude of the area. But that is absurd. The area must be a greater magnitude than its perimeter. Yet a square with the side of 2, having the area of 4, has a lesser area than it has a perimeter. The magnitude of an area cannot be less than its perimeter. The area then must be of different units of measure. That is the point that I mean to show with this. That the area then, the area of 4 of that square must be 4 of different units of measure than the 2, the numerical value of 2, which is attributed to its side. But how can a multiple of a quantity have different units of measure than the quantity it is a multiple of? Mustn't not the multiple of a quantity be a greater number of the same units of measure? This results because of the nature of continua, that they are infinitely divisible, that a line is infinitely divisible and can be divided into smaller and smaller lines ad infinitum without ever being divided into points. And likewise, an area or a surface can be divided into lesser and lesser surfaces ad infinitum without ever being divided into lines. How then can you divide a surface into quantities of length? And how can you multiply quantities of length into areas? And this is, again, at the very foundations of algebra. This is also why Euclidean mathematics uses only proportions and ratios. And avoids assigning them numerical values. Because they would be numerical values of different units of measure. And I don't see how you can pass back and forth between different units of measure by multiplication and division. Now, where do I go from here? My notes are all over the place. I've written 3+ essays that don't cover the entirety, but cover part of all these problems. We have the difference in paradigms between proportions and ratios, which allows you to correlate relations between these different orders of magnitude, as opposed to using equations, which the entire of modern mathematics subsists in a substratum of equations, every maneuver of which is a calculation or a rule for manipulating equations, which is the same. There's that distinction. There's a distinction between continuous and discrete, which is upheld in Euclidean mathematics and which is disregarded in algebra. And there are the properties of the continuum being infinitely divisible, which give rise to these difficulties, which are why numbers and intervals of different orders of magnitude can never be entirely conformed, but also why the different orders of magnitude cannot be interchangeably computed between one another. For not only are lines infinitely divisible, but surfaces are infinitely divisible, as are bodies. And if they're infinitely divisible, if surfaces are infinitely divisible, or areas are infinitely divisible, then and they're infinitely divisible into smaller and smaller areas, then to divide an area will always give you none other than an area. And if the division of an area or a surface can only ever result in smaller and smaller areas or surfaces, but never in quantities of length, then how can quantities of length be multiplied into areas? Or how can an area or a surface be thought of as a multiple of quantities of length? Again, there's this sort of inverse processes, which on both sides pose problems to algebra. For a surface or an area may be divided into smaller surfaces, which is a process of division. The quantity of the area, if there is a numerical quantity of an area that can be designated, is divided into, when divided in half, is divided into two smaller areas. And those, again, may be divided into lesser and lesser areas, without ever being divisible into quantities of a different unit of measure than of areas or squares. Never into units of length. And the question is then, how can a surface be conceived as a multiple of quantities of length? And the inverse problem, or paradox, is that when considering what meaning there might be of squaring the quantity of a line, a quantity of length, if what it means to square a quantity of length is to produce an area, yet a quantity of length having the numerical value of 2 would, if when squared, produces the area of 4, having the numerical value of 4, and the perimeter of 8 of those same units as the 2 with which the side is designated, then the perimeter would exceed the magnitude of the area. But that is absurd. And what that means is that the area must be of different units of measure. But then, how can the area be a multiple of the side? If that numerical value of 4 assigned to the area of a square having the side of 2 cannot be 4 of the same units of measure, since then the area of the square would be less than the perimeter, or the magnitude of the area would be less than that of the perimeter, which is absurd. Then the area having the numerical value of 4 must be of different units of measure. But how can the multiple of a quantity be anything but a greater number of the same units of measure? what must be meant, if there is any sense in squaring the numerical value of a line, must then be a greater line having the same units of measure, a greater quantity of the same units of measure, or just a greater line. But we find again that algebra runs into another aporia. For there is another paradox, which again applies to algebra, as algebra goes much further than just pure mathematics, than just the domains of arithmetic and of number and shape. We shall see elsewhere that especially to their physics equations, especially as to the algebra in which physics consists, when the algebraic notation of a numerical value squared does not mean an area, but a length, another paradox or contradiction results. For we will find that squaring the whole length and squaring the number of parts of the same whole equate not the same magnitude. That the number of minutes and the number of seconds that compose the same amount of time, when squared, result in different amounts of time. As also the square of a number of yards and the square of the number of feet of the same distance are, when considered as not areas but lengths, different lengths. The product is of different lengths. The same magnitude squared, if you square the greater number of lesser parts and the lesser number of greater parts, results in different magnitudes. The same magnitude squared results in different magnitudes if you square the number of minutes and if you square the number of seconds, or if you square the number of yards, if you square the number of feet. The same distance, when squared, results in different distances. When they're considered not as areas, when the square of a length is considered not as an area but as a greater quantity of length. A paradox results in this case too. This is because they're squaring the number. But not only might the same magnitude have indifferently any numerical value, since they are infinitely divisible and there can be no standard unit of measure for any continuous magnitude. But also, the same distance having a greater number of smaller measures and a lesser number of greater measures, when the same total length is squared, results in different lengths. When the same length is squared, results in different lengths. Even when the units of measure are aligned, so to speak, as meters and centimeters or yards and feet, the same 2 yards or 6 feet, when squared, will be different lengths. 2 yards is the same as 6 feet. That is the same distance. But 2 yards squared is 4 yards, or 12 feet. And 6 feet, if we square the 6 feet instead of the 2 yards, the result is 36 feet, or 9 yards. Again, 2 yards, the same distance as 6 feet, when squared, and when that's not thought of as an area, but as a length, which is the case in physics. The 2 yards squared is 4 yards, which is 12 feet, while the 6 feet squared is 36 feet, or 9 yards. Different lengths. And when the square of a distance factors into the algebraic equation of a scientific formula, think Galileo. The square of the distance fallen, the square of the time of the distance fallen. The square is meant in those cases to be a length and not an area. With Galileo's law of acceleration, this is obvious. For the square of a distance fallen can only mean a greater distance or a greater length, not an area. But most units of measure which factor into their algebraic equations in physics have no spatial significance to even possibly mean to be calculated as areas. Time, for instance, if to be squared, can only mean a greater length or span of time. And likewise with pressures, weights, tensions of a cord, and most of the rest. But when physics establishes a correlation between two things, or even aspects of things, the correlation is expressed or represented as an algebraic equation. And those equations or formulas more often than not include the relation of one variable as being the square or the square root of the other. This is because the language of physics, so to speak, is algebraic. And algebra is set up so as to calculate with primarily, besides linear quantities, quantities of surfaces and cubes, and that not insofar as they are surfaces or volumes, but insofar as they are numerically measured. As when you're just dealing with the numbers, but the numbers sometimes represent different orders of magnitude and different units of measure. Caution has to be taken that what you're doing is even comprehensible. And this is again why there are no numerical values in Euclidean geometry. Because even when the comparison is made between quantities of the same order of magnitude, caution has to be taken that the unit of measure is the same and that they are commensurate, that there is a common measure, as even between lines, sometimes there is no common measure. We find irrational numbers, as mentioned. This is just why magnitudes are compared as ratios, because there can be no standard unit of measure of a line, nor of a surface. For any arbitrarily chosen unit of measure of lines has an infinite number of parts and can be divided infinitely into smaller and smaller line segments. So when two lines or surfaces are compared, they are compared as one the measure of the other in a ratio. It's just saying as one is the other, so some number is to some other number. Or as one is to another, so another magnitude is to another magnitude. We draw proportions. And we avoid assigning numerical values to figures and their sides, except insofar as we say that a triangle inscribed within the same parallels and on the same base as a parallelogram has half the area of the parallelogram, regardless of their angular differences, and whether one is inclined more so than the other. And as said, if a numerical value were assigned to their sides, no leap could be made to equate the value of the areas for the reasons given. I'll stop there.